So if you remember in the last class, so real quick, let me just let me share this on the screen. So in the last class, we introduced this concept called the electric flux. I just want to just write down one quantity here. So we said so if you draw, so let's suppose that this is a sphere. So this is a sphere, and I have electric field lines just going through like this. So in this case, you can see that the flux now the reason why the flux is zero, because think about it, the number of lines going in is equal to the number of lines coming out. Do you guys see that? So with the number of lines, so in this case here, so always think about it as is the number in. So the reason why this is zero is because the number of lines going in is equal to the number of lines going out. Which kind of made perfect sense because we said that the area vector always comes. So let's point, so in this case here, this is my area vector here. Change the colors here. But the area vector here is negative. So that's one example. Let me show you a second example here. What if we had something like this? I have a point, a single charge in here. And you know that whenever you have a single charge, now, what is the number of field lines going out? The number of field lines coming in is actually zero. Do you see that? That there is no field lines coming in, it's just going out. So in this case, when I calculate the flux, it's not going to be equal to zero. Does that make sense? Because I don't have anything coming in, I just have something going out. Now let's show one more example, and then we'll go back to our PowerPoint. What if we have a volume that looks like this? And this is going to help you for the homework. And then let's say I have a positive charge here, negative charge here. And let's say that this is, let's say this is Q, and this is negative Q. Now, we said that an electric field always points from the positive to the negative, right? So do you see that for any field line that comes out here, there is one field line that goes in like that? And for any field line that comes out here, there is one field line that goes in. So what's the total flux here? Zero. Now, what you're going to see, and this is Gauss's law. So Gauss's law tells me that the total flux must be equal to the total charge that I have inside divided by this quantity here. So you can see that when you use this equation for the homework problems, the total charge inside this volume is plus Q plus negative Q is equal to zero. Because the total charge inside the volume is zero, that's why when I calculate the flux, I get zero. Now, in this case here, if the charge is Q here, then it means that the flux is just going to be the charge by E half. Now, one final example here. What if we have a volume like this, and then let's say we have a positive charge, a negative charge, and a positive charge.
All right, perfect. See you later.
And let's say this is Q, this is negative Q, and this is Q. Now you can see that in this case also the total flux is not going to be equal to 0. The reason is because if you think about it, for every field line that goes out here, one field line is going to come in here, right? But you also have an extra field line coming out from this extra positive charge. So I'm going to get an overall more field lines going out than coming in. And so that will give me a flux that is not 0. Okay, so with these, I want to go back to the PowerPoint to kind of show you how we can apply this to calculate some electric fields. So let me stop this sharing, and then I want to go to my PowerPoint here. Now this is just saying that, I think I said this last time, that when we calculate the flux, the area vector, so this must always point, so points at 90 degrees, and it must be pointing out. So for example, if this volume here, when I calculate the flux in this volume, this should just give me 0 because the electric field is going in here and coming out here, right? And the area here is pointing in the left, the area here is pointing to the right. So when I do everything, I end up just getting 0, just as we discussed here in the last class. Now, I think I showed you an example like this last class where you have a box, right? Then we have an electric field. So in this example, my electric field is in the X. My electric field is pointing in the X direction. So because the electric field is pointing in the X, when I calculate the flux, I should just focus on these two. The surface that is on the right side and the surface that is on the back. Remember that a cube has 6 sides, right? But because my electric field is only going in the X direction, when I calculate the flux, I don't need to use all the surface area. So I just focus on this area that is on the right side and that area that is inside right there. And then we said that since the area vector is pointing here, the area vector is pointing here again. Based on what we've seen in the previous class, this will just end up giving us 0. All right, so electric field coming in the X direction, when you calculate the flux, it should just be equal to 0. Now let's look at, so Gauss's law simply says that the flux, so again, so remember that again, this is the main point. So the flux of an electric field through a closed surface must be equal to how much amount of charge that I have in there divided by this factor right here. And we can see this because if you take the electric field of a point charge, it's just this quantity here, multiplied by the surface area of a sphere, you get this quantity. And because we know that Ke is equal to 1 over 4 pi epsilon naught 0. So if you substitute this Ke here, then you get this Q E naught. So this is the main equation that we're going to be using here. So the next thing that we're just going to do is how do we apply, so it's just application. So how do we apply these equations? And I can apply this equation to calculate, for example, All right, so let's talk about this Gaussian surface here. So the key point is that the shape is not important. So if you look at this, if I have a point charge in here, I calculate the flux here, it's always going to be Q over E naught. It doesn't matter if I calculate the flux through surface number 1, surface number 2, and surface number 3. As long as each of these surfaces here covers a charge, so each of those surfaces cover the charge, so it doesn't matter, I always get the same value for the flux. But to make life a little bit more easier, we're just going to focus on using a sphere, because a sphere is a surface that is much more easier to do calculations with. So if you look at, so this is an example. Now look at this example here. Notice that S1, S2, and S3, each of these contain a charge inside. But if you look at this other surface here, this does not contain any charge. Again, this is a body. Talk about the surface that is around. So because this does not contain any, there's no charge in here, I'm saying that the electric field going in is the same as the electric field going in. So in is equals to out. So number in equals to number out. So in this case, the flux through the surface here is going to be equals to 0, because the surface does not contain the charge. All right. Now so for example, this is what you're going to see in your homework. So for example, if you have a negative charge here, and I calculate, if you have a negative charge, phi lines always point into that negative charge. It means that, for example, for the flux here is just going to be equals to negative Q1. Now, how about if you have Q1 and Q3? Now, because phi lines are going out here, phi lines are coming in here, when I calculate the flux in this surface here, it should be equals to Q2 minus Q3. So this is not 0. This would be 0 only when Q1, Q2 equals to Q3, right? But if I just have Q2 and Q3, one is positive, one is negative, then the net flux would just be equals to Q2 minus Q3 over here. Now, how about this surface here? This surface does not contain any charge in it, so it means that the flux in there is equals to 0. So generally, we can write this equation here. So it says that the total flux must be equals to Q in. Now, Q in is the total charge inside
What is that? What is the integral symbol with the square or rectangle on it mean?
Oh, okay, that's a good question. So this is So this is just to represent, it tells you that it's an integral that is done over a surface.
Okay.
So it's not just like an integral over x. Because, for example, in calculus 1, you have a function f of x, you just do an integral, right? But this is a special type of integral that covers the surface. So it's just a symbol